Well, we did it. We got through the 7 modes of addressing, and in this video, we're going to continue with assembly language, and we're going to look at arithmetic instructions. And we'll start with the add instruction, why not? So the add instruction, its mnemonic, of course, is ADD, and it requires a source and destination. And unsurprisingly, the add instruction computes source plus destination, and it stores the answer in destination, so the destination is overridden with the answer. In the second bullet point here, we write that as source plus destination, right arrow destination. And because this is an ALU operation, the VNZC status bits are updated. And also the add instruction, of course, this can be an 8-bit or a 16-bit operation, depending on whether or not .b or .w has been applied as an extension. But let's look at an example. You'll notice here I've got some code on the left, and I've got the status register, the VNZC, on the right. So we're going to pay particular attention to those bits. Now the first few lines there you'll notice, and this video is not about addressing modes, so I'm going to presume that you know about the addressing modes, and I want to talk really about the add part of this. So we move the number 371 in decimal into R4, we move the number 465 decimal into R5, great. Now you'll notice on the add instruction, we've got add.w, and so that's going to add R4, the contents of R4, with the contents of R5 and store it in R5. So the addition is 836 in decimal. So if we looked into register R5, that's what we would see, 836 in decimal. Now, did that give us a 2's complement overflow? No. That does not give us a negative number. That does not give us 0, and there was no carry out. Those bits will be all 0 there. Let's look at the next pair, or I guess not pair, but the next set. We've got, we're moving the number FFFE into register 16, and then on the next line, we're going to add 1 in hexadecimal with that number in R6, and then it gets stored, the result is stored in R6, register 6. So here, FFFE plus 0001, that gives us FFFF. So in this case, we have the negative flag goes up because F, if we expanded it into binary, is 1111, and so this number begins with a 1. That is, it's got a 1 in the most significant bit column, and so that's a negative number. Okay, the next example here. Let's move now FFFF into, let's say, R7, and then let's add 1 to it, and you'll notice the add instruction. This result will be stored back into R7. So again, I want to point out that the data FFFF will be lost upon executing that add instruction. So here, when we add FFFF with 1, we get 0000. In this case, we get a carry out. Think about how you would do this operation on pencil and paper. You get a carry out. So we would have C equals 1 after this operation. We would have the 0 flag go up because the answer is 0. Then the negative flag would go back to 0 at this point because that is not a negative number. Okay, the next set. Now here I want to highlight that we're appending the byte or the .b extension there. So these will just be bytes. So 255 in decimal gets stored into R8, register 8, and the number 1 in decimal into R9. And then we add R8 with R9, and again I want to point out the result is stored in R9. Now with a byte, we cannot capture or represent 256. So because this is a byte operation, .b, then 255 plus 1 is 0. In this case, the status bits will stay the same then. So we'll still have 0 and we'll still have a carry out. Okay, the next set here, -1 plus 1, and that result will be stored back into register 10, for example. So -1 plus 1, of course, is 0, but I want to point out that -1 is FF in hexadecimal, and 1, of course, is 0, 1. So then you can think about, like, when you do that addition, you're going to get a carry out, right? So C will be 1. You're also going to get the answer 0, of course, and so Z will stay 1. Okay, and then finally, the last set there, we're going to add 127 in decimal with 127 in decimal, which is 254. Now, this is a byte operation, and so when we do this, of course, we get 254, but we get a carry out of 0, right? There's no carry out. And the answer is not 0, certainly not. But if you were to do this with pencil and paper, or let me say, how about with signed bits? 8 bits is not enough to store the result, right? The largest number that we can store in 8-bit 2's complement is 127, or that we can represent is 127. So in this case, when you actually do the pencil and paper, you'll see that you'll get a negative number as an answer, and then because we have a positive number plus a positive number and we get a negative number, then we know that we had 2's complement overflow, and we'll get also V equals 1. Okay, the add C instruction, it requires a source and a destination, but it also computes source plus destination plus the carry bit and stores the answer in destination. So C is the carry bit from that status register, as we were talking about. And so in the second bullet point here, we would write source plus destination plus C gets stored as dest. Because this is an ALU operation, the VNZC status bits are updated, and of course we can do this on 8 bits or 16 bits. But we might ask the question why? Like, why do we want to add the C bit to this? And of course the answer is to allow our 16-bit CPU, for example, to process larger numbers like 32 bits. So you do that 16 bits at a time, you do the least significant 16 bits first, and then the most significant bits, but you have to remember if there was a carryout from the least significant bits. That's when we want to add C. So let's look at an example. Okay, we're going to add those two add-ins there, which I won't redo, but they're shown at the top, and we're going to keep track of the VNZC status bits. Now when you do it by hand, and I really encourage you to do this by hand to see if you can get this, you get F4832221 in hexadecimal. I guess let me back up. The top 3 instructions are just move instructions, and again, this video is not about addressing modes, so I don't want to go over those. I want to go over the next group where there's an add instruction there. Okay, so what this add instruction is going to do is going to add the least significant bits first. So it's going to add the least significant 16 bits, FFFF, with 2222 in hexadecimal. And again, I encourage you to do this on your own by hand, and what you'll see is you get 2221 with a carry out. So now you'll see it to the right in the status register, the carry out bit is 1. And notice I'm using just the add command, not add C. That's because we started at the least significant 16 bits. Now, the most significant bits, we're going to add E371 with 1111, but because that's the most significant 16 bits and we had that carry from the previous stage, we want to add that carry to it. So we're going to use add C, the add C instruction. And I encourage you to do this by hand. When C is 1, we add those together and we get the correct answer, F483. Now when we do that, we do not get a carry out. So then C will go back to 0. And because our answer is negative, N will be 1. It's negative because F, the most significant digit, is 1111 when it's expanded into binary. So this number begins with a 1, i.e. it's negative. Okay, then of course there's the sub instruction, which, big surprise, it subtracts. And it does this, it requires the source and the destination, and it computes the destination minus the source and stores the answer in destination. So the second bullet point there, we would write dest minus source, right arrow dest, to just summarize that operation. Now, an important point here is it does not have a separate subtractor circuit. So what it does is it just, that is the microcontroller. The microcontroller uses the adder circuit to compute destination plus negative source. Because that's an ALU operation, the VNCC status bits are updated, and of course this can be an 8-bit or a 16-bit. Let's look at an example. Simple example to the left, status register at the right, so let's say that they're all cleared at the beginning. Again, I don't want to go over what the move instructions do particularly. So I'll just point out that the sub instruction is subtracting, remember it's destination minus source, which is, I don't know, for me anyway, it's hard to get used to. I feel like it should be the other way, but it's not. So this one is taking FF, and notice that the .b has been appended, so these are bytes. It's taking FF minus 0, 1, and that gives us, of course, FE. Now, the answer is negative here. Of course, F, as it is expanded, is 1111, so N is equal to 1 in this case. Also, and I encourage you to do this by hand. When you do the subtraction, well, of course, when you do the subtraction, you don't require a borrow into. And so because there's no borrow into, C is equal to 1. And why that is, that seems maybe a little bit backwards, but it is. It's the opposite of addition, right? Subtraction is the opposite of addition. So in this case, when you don't need a borrow into, then C will be 1. And I'm just going to leave that at that. Once you work these things out by hand a little bit, you'll start to convince yourself of this. But just remember that C is going to be the opposite. If I did not need a borrow into, C will be 1. Okay, let's look at this example. This one will subtract 1 minus FF, so the opposite, and store the result in R6. In this case, when you do 1 minus FF, the answer is 0, 2. Again, if you want to work that out by hand, please do. I encourage you to do so. In this case, of course, the answer requires a borrow into. You can't subtract 0, 1 minus FF without borrowing into to allow make 0, 1 bigger. So you need a borrow into, so C will be 0 for that. Also, the answer is positive, so that status flag will change back N equals 0. All right, the sub C instruction is similar to what we've been talking about here. It requires a source and destination, and it computes destination minus source minus not C for reasons why we've already talked about. It's like the opposite of adding. And it stores the answer into the destination. It does utilize the adder circuit again to compute it, and it's an ALU operation, so the VNZC status bits are updated. So let's look at this example here. So we're computing the difference of those two numbers, and I've got the status register again to the right. I don't want to talk about the moving instructions, so we'll go down to the next group, the second group, where there's the first subtraction operation. So here we're subtracting 1 F with minus 2, 2, 2, 2. The answer is FDDD. So what we're doing is subtracting the least significant 16 bits. Okay, because this is a 32-bit operation in total. So we're subtracting the least significant 16 bits. Now to do this operation, a borrow into is required, right? Think about that for a second. We've got a 1 at the most significant digit and then a 2 in the subtrahend. So we're going to need to borrow into, so C will be 0. The result, F, can be F at the most significant can be expanded, and so this is a negative answer. Now when we compute the most significant 16 bits, E465 minus 1111, we need to remember that there was a borrow into required, so we're actually going to subtract 1 as well. That gives us the correct answer, D353. So we're subtracting 1 because previously C was a 0, right? C was a 0, so it subtracts not C. So it's subtracting 1. Now when we do that operation, no borrow into is required, so C goes back to 1. And then we have the number D353, which again, D is negative, so the negative flag goes up. Again, I encourage you to work these things out by hand if you want. Please do that. All right, so we looked at some arithmetic operations here. Next time, we're going to keep with the assembly language and ALU operations, data manipulation, and we're going to look at how logical operations can be used for bit masking. Thank you.